All right, this chapter is on gases. We will be talking about pressure, volume, temperature, and moles. In part 2 of gases, we will look at reactions that take place and stoichiometry associated with molecules that are reacting in the gas phase. So we'll start here with just some basic definitions, and we'll start with pressure. Pressure is going to be defined as force per unit area. So you can think of gas phase molecules striking, the inner surface of the container, with a certain force over a given area. And to give you an idea of the magnitude of the force associated with the atmospheric pressure, we'll start with just a simple calculation for pressure. So it's defined as force divided by area, or force per unit area. That's one of the definitions. And force is going to be equal to mass times the gravitational constant G, which is 9.81 meters per second squared. So G is 9.81 meters per second squared. You can Google this, or maybe you learned it in your physics classes. It's an acceleration that's particular to the gravitational force. It has a certain number. It'll go with a speed of 9.81 meters per second for every second. All right, and then area pi r squared, and in this case we're looking at a coin. So here's a table, and you've got a little coin on it, and you want to calculate the pressure that the coin exerts on the table. And the radius of the coin is 9.3 millimeters, and the mass of the coin is 2.5 grams. So we can use these equations to calculate it. First, we can calculate the force, and that is going to be equal to mass times g, or acceleration due to gravity, and the mass in kilograms, we got it in grams, 2.5 grams, so this is going to be 0.0025 kilograms, or 10 to the minus 3 kilograms, and then 9.81 meters per second squared. So the force is 2.5 10 to the minus 2 kilogram meter per second squared. And usually I ask in class, does anyone know what the unit kilogram meter per second squared is? And the answer is going to be Newton. Newton is the SI unit for force. And Newton. All right, so then that's the force, that's the numerator in that expression for pressure. The area pi r squared, and we're given that the radius is 9.3 millimeters. So this is going to be pi, we'll just say 3.14. You put it in your calculator, you get higher sig figs. 9.3 times 10 to the minus 3 millimeters. Yeah, converted that from millimeters, and that'll be squared. So this is 2.7 times 10 to the minus 4 meter squared. All right, so then you want to divide those two numbers. Pressure is going to be the force, 2.5 10 to the minus 2 kilogram meter per second squared, divided by area, 2.7 10 to the minus 4 meters squared. And so this pressure will be equal to 93 kilogram per meter, and you have seconds to the -2. Okay, so this is going to be the SI unit for pressure, and the name of it is Pascal. So this is 93 pascals, 93 P. Pressure is PA. Pressure is 93 pascals. All right, so it's just a simple calculation. Think about a coin on a table. The pressure that the coin exerts is 93 pascals. I'm sure you can argue that that's not a very large pressure, not a very high pressure associated with the coin. All right, so Pascal, you can see here, is one of the units. We are used to talking about pressure maybe in PSI, pounds per square inch. Oftentimes you see that in the news, in your readings. If you have a tank of gas, there'll be a regulator that usually is calibrated in pounds per square inch, as well as other units. But the Pascal certainly is an important one. That's the SI unit. And then we talk about inches of mercury when we're talking about the weather, the height of the mercury in a barometer, 29.92 inches. And then we talk about the atmosphere as well. So let me define. If you go back and look at this table again, you see that 1 atmosphere is 760 torr. 1 atmosphere is 760 millimeters of mercury. 1 atmosphere, this would be the English or American system of units for pressure, 14.7 psi, pounds per square inch. And then let's see, if you went from millimeters to inches, you'd have 29.92. So all this is all about that, using the barometer to measure the pressure. And then these numbers come from the calculation, like the coin on the table. And you come up with the relationship between 1 atmosphere and pascals, or you can write it in terms of kilopascals. And these are going to be important numbers as well, because all other countries besides the US and probably Britain, although Britain uses both, will use pascals for pressure. So if you look up some manual for an instrument that's built in England, for example, the pressures will be in pascals or kilopascals. So then, let's see, you can remember that 1 atmosphere is about 100, kilopascals, something like that. Or 1 atmosphere is 10 to the 5th pascals. That's a good one to remember. Some of this, and we'll come back to that table. Here you have a figure which shows imagine you just have a tube in your hand. It's sealed at the bottom and it's open at the top. And you pour liquid mercury into it and you completely fill it. And then you put your thumb over the top. You really wouldn't want to do that because mercury is toxic, but your gloved finger, for example, you can put on the top. And then you flip the tube upside down and put it under the surface of this dish that contains liquid mercury. So maybe the end of it's here and your thumb is on the opening of the tube. So you pull your thumb away, and what do you see? That some of the mercury is going to drop down into the dish, into the pool of mercury liquid. So why does that happen? It's just a pure gravitational effect. Gravity is going to try to pull that liquid out of the tube. But the reason why all of it doesn't fall out is because the atmospheric pressure is exerted on the surface of this pool of liquid, and its effect is to kind of push it right back up. So gravity's pulling it down, and then the atmospheric pressure's forcing it back up, and it'll come to some position, some equilibrium position. In this case, it's here. And what you want to do is just take a meter stick and hold it next to it like this, And then your meter stick will be calibrated. If I draw it, it won't look that good. Let me try. So you have a meter stick here, and then the meter stick's going to be calibrated. And the actual height, this will be the top of the meniscus here. Mercury is kind of the opposite of water. It pulls down instead of up when it hits the surfaces. And so this height, measured with the meter stick, is going to be 760 millimeters of mercury. And that will be the situation if it is at 0 degrees C. So 0 degrees C, and it is at, if your barometer happens to be at sea level. All right, and then what we'll find is that the height of the column of mercury that supports the pressure of the atmosphere is 760 millimeters. And I believe that, no, it's not. So let me just write it underneath. The height of a column of mercury that supports the pressure of the atmosphere is 760 millimeters under the conditions of sea level and 0 degrees C. All right, that is called 1 atmosphere. So 760 millimeters of mercury is defined as 1 atmosphere. And also Torricelli was the scientist who did these experiments, the Italian scientist who did that. And so we also use the term 760 torr, which means that a millimeter of mercury is equal to 1 torr. All right, so we use those units interchangeably. Okay, this setup is for measuring pressures of gases in the laboratory. Here we use a manometer instead of a barometer. The barometer was illustrated in the last slide. Manometer is the one you would use in the lab. Nowadays we don't use manometers so much because it's toxic. The mercury inside is toxic. But still, to understand how they work is valuable. And in this case, the setup is that there is one of these tubes, and both sides are exposed to the atmosphere, so the tubes are open, and then you put mercury in there, and it's going to fill up to the same height on both sides. You just pour it in and it'll fill in like this. Okay, so then next step is to take your manometer and hook it up to a gas through some tubing. And so the tubing would be attached here. And then if there's a stopcock here, you can open it up and then some of the gas will move out. And as it does, it'll push down the air, the 1 atmosphere pressure of the atmosphere, and then it'll push it down even more because the pressure here is above atmospheric pressure. And it'll move it up on this side. So the difference in the heights of the two columns, mercury in the 2 columns, is going to be the height, and the height will correspond to the pressure of the gas over here. It's actually the pressure of the gas plus the atmospheric pressure that was already in this side. That's called an open-end manometer when you have to include the pressure of the atmosphere. So the pressure of the gas then is equal to the pressure of the atmosphere plus the pressure associated with change in height of the system. So I'm probably not going to ask you questions about the manometer. There's 2 different types. This is the open end. There's another type called closed end, which I prefer to work with. Basically, you just have a vacuum in this part here. So when you open this up, the part that gets depressed here is only due to the gas and not the added atmosphere. But anyway, I usually tend not to worry too much about this since we use different detectors now for pressure these days. All right, but let's keep it simple here. This one is going to be the first of several individual gas laws, and in the end we're going to put the individual gas laws together to come up with the ideal gas law. So Boyles Law, notice that there are changes in volume and pressure here, and one of the keys to making sure you're dealing with the correct equation, Boyles Law is going to give you the relationship between pressure and volume, but the temperature of the system stays the same. So it's constant temperature. That's what you want to look for. And what do we see here? So you have a gas in a cylinder, and then it's got this piston. The piston can move up and down. Sometimes you can put little stops on it so it doesn't move after you put it in the position that you want. In this example, you just put different weights on it, 1 kilogram and 2 kilograms. So that'll just hold it in a certain place. And you start with the system measuring, this is just a meter here to measure the pressure, not a manometer, 1 atmosphere pressure, and then you have this volume right here being equal to 1 liter. Now you're going to change the position of the piston, and you do it so that the pressure now is 2 atmospheres. You want to put the weights on until the pressure doubles, and then when that happens, you can determine that the volume is half what it was before. So you see, when you increase the pressure on the system, the volume decreases. There's going to be an inverse proportional relationship between those two. So if you do a graph of pressure versus volume, this is in cubic inches, notice inches of mercury here, and shouldn't matter too much. Let's see, this number might be around 120. Let's pick a different one here, 60. Yeah, we could go from 120, which is about 12, down to 60. If this were correct, that would be double, so it would be 24. So as you increase as you decrease the pressure, then the volume is going to increase, and it would go from 12 to 24 in that example. And so you can keep, with the same gas, you can keep changing the pressure and just measuring the volumes and get a series of data points here. This, again, is associated with constant temperature. So this curve is called an isotherm. So this is associated with, T1. Now, if you change the temperature of the same gas in the same container, you're going to get a second graph. And if you increase the temperature, you're going to get another isotherm. So in other words, it's parallel at every point and has the exact same behavior in terms of pressure and volume, the inverse relationship there. And if you did a T3, it would look like that. So these are the isotherms. This one would be T3. The isotherms associated with the gas. Work with this data, not, this would be a raw data, pressure versus volume. But this is referred to as a hyperbolic curve. So you can, and it's not as useful as the linear relationship. So since they're inversely proportional, I guess I'll write it here. So what we've seen so far is that pressure is going to be inversely proportional to volume. So as you increase the pressure, the volume goes down. If you increase the volume, the pressure goes up. So we can say that pressure is equal to a constant times 1 over V, and multiply both sides times V, you're going to get PV is equal to a constant. So you could take one of your data points on the curve. So you get your curve like this, P versus V. And you can take one data point here. You can call that one P1, V1. Take another data point, P2, V2, like that. But the product of P and V for any given data point is going to be equal to this particular constant, this particular numerical value. So you can say P1, V1 is equal to a constant. P2, V2 is equal to the same constant associated with the isotherm. And then P1, V1 is equal to P2, V2 at constant temperature. And that is Boyles Law. All right, so you get the inverse relationship here, but what this graph is showing us is that if you plot P versus 1 over T, oh, I'm sorry, 1 over V. So if you plot P versus 1 over V as opposed to P, this is PV here, this is the graph you get. So pressure versus inverse volume, and you can see that it's linear. That's just an easier equation to work with. And you, of course, have y equals mx plus b. And x and y are going to be your P and inverse volume variables. You can determine the slope there. You can determine the intercept. And then you can, using one value of inverse volume, you can predict any pressure associated with it using this equation, once you know the slope and the intercept. One thing here. All right, so in terms of a calculation, you got your constant temperature. You have 100 mils. And what is the final volume if the pressure goes from 760 to 800? So you can just kind of, the best thing to do with these gas problems is just to make a list. P1, V1, P2, V2. So P1 is 760 torr, and V1 is 100 milliliters. Change to P2, 800 torr. And V2 is what you're looking for. So you know your equation, P1, V1 is equal to P2, V2. Solve for V2, P1, V1 over P2. And things should work out fine. So P1, 760 torr. V1, 100 ml divided by P2, 800 torr. Solve for V and it'll be in milliliters. And 95 milliliters. So would you expect that? If the pressure goes up slightly, the volume's going to go down slightly. So the answer is yes, you would expect that. All right, so the next of the individual gas laws is called Charles' Law. And this one is going to be associated with constant pressure where the volume and the temperature are changing. So the volume is directly proportional to the temperature. And you can do a very simple experiment. You can just blow up a balloon, certain volume, and then stick it into an ice water bath. And as the temperature of the gas decreases, what you'd find is that the volume of the balloon decreases. The balloon will just shrivel right up to very small volume. And you can Google Charles' Law and look at videos. Go to YouTube and look at videos on that. It's pretty cool. So then here we have volume is proportional to temperature at constant pressure. All right, and let's see what the next graph is. So in this graph, you have an ideal gas, just some typical gas like oxygen or nitrogen. And what we're seeing here is that if you're plotting T here as temperature in degrees C, okay, then as the temperature decreases, the volume decreases as well. So you see this decrease in volume as you're decreasing the temperature. Now, if it's an ideal gas, it'll stop. And actually, no, I'm take that back. If it's an ideal gas, it should, in principle, in theory, it should keep going. It won't, but it'll get. You can get them close. Like helium, you can get pretty close to zero volume, which is kind of an imaginary construct. But anyway, let's just, as you decrease the volume as far as it'll go, the temperature eventually, in theory, you can just extrapolate the points. We'll go down to negative 273.16 or 15. Okay, so then we call that Kelvin. This is defined as 0 degrees Kelvin, and that is the absolute temperature scale there in Kelvin. So if you're up here, let's say that this is 0 degrees C here, then this will be equal to 273.15 or 16. I always use 5 Kelvin. Now, if the gases were real, we haven't talked about the difference between ideal gas and real gases yet. The ideal gas is just kind of a laboratory construct. We imagine that molecules, when they pass each other in space inside the balloon or inside the gas phase container, don't interact with each other. So there's no attraction or repulsion between the molecules as they pass by each other. So that's kind of the condition for the ideal gas. And if the temperature is high enough, then real gas molecules, which do have those intermolecular forces, behave ideally because they're moving so fast. And if the pressure is low enough, there's not so much space in between the molecules that they don't even interact that much anyway. So you can say real molecules behave ideally under conditions of, let me write that down. So, ideal gas when the system is at high temperature and low pressure. But if you decrease the temperature and increase the pressure, then the molecules start interacting. We call that the real gas situation. So if it were a real gas, you'd start out the same. The real gas volume is going to decrease as you decrease the temperature. You're going to get to some, it might be 0 degrees, it might be lower. Most gases are lower than that. But all of a sudden, you got condensation. All right, that is the property of a real gas system, where the volume, where the gas goes to liquid, so it undergoes condensation. If you continue to lower the temperature, you get a little small change in volume, but not a lot. And then when it goes to the solid, you'll get a little bit more of a decrease in volume. And as you continue to, decrease the temperature, you might get something like that. So it's not going to hit 0 degrees Kelvin, and the volume is never going to be 0 milliliters or liters. But so this would be for the real gas, and this is more like the ideal gas. All right, so then what next? We're going to say that Charles' law, I guess I'll just have to write them out. So for Charles' law, volume is proportional to temperature when the pressure is constant. So if volume is proportional to temperature, we can say volume is equal to a constant times temperature. And you can say V over T will be equal to a constant. And you can just take points from the graph. For any data set, you got a temperature and a volume, T1, V1, T2, V2, and so on. So you can end up with let's see, V1 over T1 will be equal to a constant, and V2 over T2 will be equal to the same constant. So you can just do that. And this would be Charles' law at constant pressure. All right, now we can do a quick calculation for Charles' law. And see if I got my numbers here yet. All right, so how do you know that it's a Charles' law problem? You want to look what's constant, because you got pressure, volume, and temperature. Which one of them is going to be constant? Then it should be the relationship between the other two. So you have volume here and temperature, V1 over T1, V2 over T2, constant pressure. So we're going to use that. And we're going to solve for volume, V2. So V2 will be equal to V1 over T1 multiplied times T2. And you can make a list here. You got V1, T1, V2, T2. This is the one we're looking at. V1, 250 ml. T1, 27 degrees C, and you never, ever, ever want to leave anything in degrees C for this entire chapter. You've always got to convert. You got to add 273.15 Kelvin to get, let's leave off the 0.15. We'll just say 273, and this will be 300 Kelvin. And you don't need that. That little zero there, you just say Kelvin equals T1. And then T2 is 35 degrees. This is going to be equal to 308 Kelvin. So 35 plus 273 is 308. All right, so then we can plug it in. We're going to solve for V2 here. Let's see, you got 250 ml for V1. T2 is 308 Kelvin. T1, 300 Kelvin. And, excuse me, solve for V2, and it's 256 milliliters. See if it makes sense. So if you increase the temperature from 300 to 308, the volume should increase as well. So it goes from 250 to 256. So that is in the right direction. Small changes, but could be much larger depending on the numbers that you're working with. All right, so next is law of Gay-Lussac. This one has constant volume. Again, it's pressure, volume, and temperature. This time we're looking at pressure versus temperature. We're going to find that the Gay-Lussac's law is going to be similar to Charles' law. P1 over T1 is P2 over T2 with constant volume. So you could work that out. All right, and the next law, Avagos Law, says that volume is proportional to the number of gas molecules if you have constant pressure and temperature. So for this one, you can add volume. Let's say you're just blowing up a balloon, for example. As you increase the number of moles of air that you're blowing into the balloon, the volume of the balloon's going to go up. So that's kind of easy. Now, another part of the Avagos Law story is that back in the day, let's say he was looking at hydrogen plus oxygen forms water, all in the gas phase. And they knew at the time that stoichiometrically hydrogen and oxygen combine in a 2-to-1 ratio to form 2 moles of water. And what he realized, so in other words, 2 moles, 1 mole forms 2 moles. All right. And the question was, what about the volume? So he saw if you combine 2 liters of hydrogen with 1 liter of oxygen, okay, what do you think he got? Did he get 3 liters of water or did he get 2 liters of water? And the answer is because it's a chemical reaction that takes place, you just can't add up the volumes of what you started with. There's no conservation of volume here. The answer is 2 liters. So here you see the idea that the volume is proportional to the moles, and whatever the moles are during the reaction, it goes down to 2 moles, then the volume will be proportional to that. All right. Then this is another figure associated with the volume and the moles of gas. This one's different though. This is molar volume, and we say that the volume associated with 1 mole of a gas at STP conditions is equal to 22.4 liters. Let me write this down. The volume of a gas, and this is going to be the ideal gas. The volume of an ideal gas, actually let me change it again. The volume of 1 mole of an ideal gas at STP conditions is 22.4 liters. So STP conditions then is standard temperature and pressure. So standard temperature would be 273.15 degrees Kelvin, which is equal to 0 degrees C. So standard temperature for gases is 0 degrees C, which is 273 Kelvin. When we get to the thermodynamics chapter, then we'll find that standard temperature is 25 degrees C, which is 298 Kelvin. But for gases, this is the standard temperature that's referred to. Then the standard pressure is 1 atmosphere. Okay, so the volume of a mole of ideal gas at standard temperature and pressure conditions is 22.4 liters. So look at the figure again, and you can see that it's the same for the 3 gases. That volume is independent of whether it's helium, xenon, or methane. So an ideal gas doesn't matter. It doesn't matter if it's ideal helium, ideal xenon, ideal methane. It'll have the exact same properties and therefore the same molar volume. Now, if you looked at gases, all right, so if you go back now to this slide, the volume of an ideal gas occupies 273 Kelvin in 1 atmosphere. The volume's 22.4 liters. That's our definition right there that I wrote down. Next slide. You can see that it's not exactly 22.4 liters as it would be if it were ideal. So real gas molecules have slight differences from the 22.4, and this is a measure of the non-ideality of these substances. Notice something like ammonia, and if I had water in here as well, you'd see a bigger deviation from 22.4. Ammonia and water have strong interactions between each other. It takes a little bit more energy to break up those interactions. Those are called hydrogen bonds. So just the volume's a little bit smaller due to their close interactions. All right, so that's the end of the first part. Gases 1 and gases 2 gets a little bit more complicated. So this is your introductory material for this chapter.